So hi everyone, and welcome to Quantum Science Seminar number 64. And it's all going to be about neutral atoms in tweezer arrays and Rydberg and fun things that you can do with it today. Our speaker's going to have two breaks for questions in the middle of his talk, as well as one at the end. So please, throughout the talk, send us your questions either in the YouTube live chat or at quantumscienceseminar@gmail.com. Do remember there's a 30-second delay between what's happening live here and what you're seeing on YouTube. So if we don't answer your question immediately, it might be in the next slot or so. With that, I will hand over to Oriel, who's going to announce our speaker today.
Yeah, thank you, Andrew, and welcome everybody. It is a real pleasure today to introduce our speaker, Hannes Pichler. So Hannes studied physics in the University of Innsbruck, and then he did his PhD under the supervision of Peter Zoller on a thesis on atomic quantum simulators, on detecting entanglement and designing open many-body dynamics. Then he went as an item postdoc to Harvard in the group of Michel Lukin, where he stayed around 4 years. And then he went for a year postdoc at Caltech under a Moore postdoctoral scholar. And in there, he collaborated with a group of Manuel Enders. And in 2020, we were lucky to hire Hannes in Innsbruck as a professor in physics at the University of Innsbruck and as a group leader at the Institute for Quantum Optics and Quantum Information of the Austrian Academy of Science. So the research interest of Hannes and his group is on theoretical quantum optics and quantum information, atomic physics, Rydberg physics, and many-body physics. And he has contributed already on many important results, both on the theory side and also in collaboration with experiments, such as measuring entanglement entropy in many-body systems, quantum optics with chiral spin networks, photonic circuits with time delays and quantum feedback, quantum computation with, theory, also then theory on Rydberg arrays for quantum simulation with the famous papers on the experimental side of probing many-body dynamics on a quantum simulator and generation and manipulation of Schrödinger cat states in Rydberg atom arrays, among others. So Hannes got several fellowships, the ITAM Fellowship, Futura Award in Italy, the Moore Fellowship, and recently here in Europe, the ERC starting grant this year. So it is a real pleasure for us to have you here, Hannes, and we look very much forward to your talk.
Okay, thank you, Ariel, for this very nice introduction, and thanks for sort of the committee here that organizes this quantum science seminar for the service that you do to the community. It's a real pleasure for me to present here. I think I have to share my slides now. Does this work? Okay, perfect. Yeah, what I would like to do today is to to give a sort of overview introduction about the physics of Rydberg atom arrays, and I would like to do that on a couple of examples of the work that I've done over the last couple of years, together with sort of in an collaboration with an experiment at Harvard and MIT that is sort of led by Vladan Vuletic, Markus Greiner, and Michel Lukin. So I had the pleasure to work with this experiment now for many years as a theorist and in an ongoing collaboration. And I hope that sort of today's seminar can convince you that there is a lot of interesting physics that can be explored with these Rydberg atom arrays. So in general, this is sort of the topic of this talk is in the field of quantum science and technology. And what I find exciting about this field is that we're really now at the quest for controlling the quantum world, in the sense that over the last decades, people have developed the tools to isolate and control individual, simple quantum systems, single quantum systems in all their degrees of freedom. And nowadays, we're really at a time where we can start, assembling quantum many-body systems, controlled quantum many-body systems in a bottom-up approach, where we combine individual quantum systems and make them interact, and build essentially artificial quantum systems with engineered quantity in a bottom-up approach. And this is really a new paradigm where we can explore quantum many-body physics with a novel approach experimentally, but it also opens a lot of new questions and opportunities for theorists to look at new questions. And as you will see in the talk, for many of these engineered quantum many-body systems, the line between sort of quantum simulators and quantum computer really becomes very blurry. And I think there's a lot of interesting physics to be explored at the interface between these two fields. Okay, so that said, I'm going to talk about essentially a specific platform of these, artificial quantum many-body systems, which is Rydberg atom arrays. These Rydberg atom arrays, I will, talk a little bit more about sort of the basic physics of these systems. But essentially, what they are is, one uses optical tweezers to trap individual atoms, using an AC Stark shift, and then uses the internal electronic degrees of freedom of these atoms to realize a variety of spin models. And these Rydberg atom arrays have a couple of very nice features. First of all, they are sort of inherently scalable, so one can readily assemble large numbers of such atoms in these tweezers. These atoms have very high coherence, very good coherence properties. They can interact strongly via Rydberg interactions, and I will explain in a second how that works. There's a very large degree of programmability in this system. So with these atoms, you will see one can realize these type of spin models, and one has very good control over many of the parameters that enter the Hamiltonian that describes the dynamics of the system, simply by tuning parameters of lasers to drive these atoms, or using the possibility to place these tweezers in different locations, and in that way generate different Hamiltonians. And that's complemented with sort of in situ measurements that people have developed over the last decade in quantum microscopy, where you can really read out the individual electronic state of this atom on each side in situ. And what I would like to do today is to tell you how one can combine these features to study different types of many-body physics, but then also sort of go over more and more into sort of quantum information processing applications. Okay, so what I would like to start out with is with some sort of very basic introduction about what's a Rydberg atom and what are Rydberg atoms and optical tweezers. So essentially, as I said, you trap in these optical tweezers, you trap an atom at sort of the point of maximum light intensity. And what we're going to do is we're going to use the internal electronic degrees of freedom of the atom. So this has a lot of internal energy states. And when we talk about Rydberg states, what we really mean is sort of electronic states with a very large principal quantum number. So principal quantum number n much larger than 1. Typically, when we talk about Rydberg states, we are interested in principal quantum numbers somewhere between 50 and 100. So that's the order of magnitude. And to explore, and these Rydberg states, they have very particular properties. Of course, if you excite an electron of an atom to a highly excited Rydberg state, first of all, the electronic orbit or the wave function of the electron expands, and it actually, the size of this electron orbit grows with the principal quantum number squared. And that leads to the fact that these Rydberg states have a very large transition dipole moments to other Rydberg states, which also scale with the principal quantum number squared. The reason is really there's an electron that is very far away from the core, and this creates a big dipole in the semi-classical picture. You can really see that this is why these Rydberg states have a large dipole moment. One other thing that is sort of a little bit counterintuitive maybe is that these Rydberg states also have a very large radiative lifetime, so lifetime against spontaneous emission, which also increases with the principal quantum number, and it actually increases with the principal quantum number to the third power. And sort of the intuitive explanation of why that is because if you have a Rydberg an atom in a Rydberg state, it means that the electron is very far away from the core, and sort of in a semi-classical picture is on an orbit very far out, where it doesn't really feel a very strong acceleration. and if the electron is not strongly accelerated, it will not radiate very quickly. Okay, so that's kind of Rydberg physics in a sort of very nutshell. So how do we explore this Rydberg physics? Well, essentially, typically what you have is you have an atom that is in some electronic ground state where you can prepare it, for example, by optical pumping. And then you use a laser, maybe a single photon transition or a 2-photon transition to couple this, ground state atom to one of these Rydberg states. And you can, select which Rydberg state you talk to by basically choosing the laser frequency and polarizations of your light. And in the end, you can think about this atom as a two-level system where your ground state is something that I call 0 in the following, and your Rydberg state is something that I call 1. And these two states are coupled by this laser field, which is specified by a Rabi frequency, and the detuning, where the Rabi frequency is just proportional to the laser electric field strength, and the tuning is the mismatch between the laser frequency and the transition frequency from the ground state to the Rydberg state. So in a rotating frame, the Hamiltonian is very, very simple. Of this single atom, it just contains this transition from 0 to 1 and this detuning term. And what it does is essentially induces Rabi oscillations, and you can in experiments, for example, this is data taken from Misha Lukin's group, really beautifully show that you can perform coherent Rabi oscillations over very, very many cycles. Of course, the physics becomes much more interesting once you start talking about more than one atom. So if you have two atoms in two separate optical tweezers that are separated by some distance x, then they can interact. And the way they interact is because two atoms, if they're both excited to a Rydberg state, they have very strong induced dipole-dipole interactions. Each Rydberg atom has a very strong has large transition dipole matrix elements to other Rydberg states. So if you have two atoms in two Rydberg states, induced van der Waals interaction can lead to this very basic behavior of the interaction energy. So you get a shift for when two atoms are both in the Rydberg state, and it depends on the distance of these atoms to the 6th power, and the strength of this interaction grows actually with the principal quantum number to the 11th power. So it's a really dramatic dependence on the principal quantum number that has to do with the fact that you have these large transition dipole moments, but also with the fact that sort of the Rydberg states become closer in energy. But if you plug in the numbers that for typically Rydberg states that are accessed in experiments, and typical distances which are sort of micrometer scale here, then this interaction energy is on the order of megahertz, which is really an energy scale that is sort of comparable with Rabi frequency, and therefore we can go into this strongly interacting regime. Okay, so to just give you a very sort of quick overview of what this van der Waals interaction actually does, consider this situation. If you have two atoms separated by a certain distance in these two tweezers here, and you place one of these atoms in the internal ground state, what happens then is that the second atom doesn't really feel the presence of the first atom, because if the first atom is in the ground state, these Rydberg interactions are not there, and neutral atoms in their ground state don't interact over these long distances. So if you drive this transition with a laser from the side here, with the frequency that is resonant with the transition from the ground state to the Rydberg state, you will just drive a transition of this atom here. On the other hand, if you place this first atom into the Rydberg state, what happens is now the energy of this second Rydberg state here depends on the distance, has a dependence that is given by this formula. So if you bring these atoms close together, this transition frequency will become off resonant. The transition frequency will be so large that the laser is off resonant with the transition of the second atom to the Rydberg state, and you no longer can excite a second atom to the Rydberg state if there is a first atom already in the Rydberg state close by. And this is sort of this famous Rydberg blockade effect. And we can define a Rydberg blockade radius where this effect sort of happens, which is defined by sort of the distance when, where two atoms, where the interaction between two Rydberg atoms is comparable to the Rabi frequency, such that if you're closer than this Rydberg blockade distance, a laser with this Rabi frequency cannot resonantly excite the second atom. So that's the main basic Rydberg blockade mechanism. And if you now build sort of a many-body system, in this way, by simply having many of these tweezers filled each one with a single atom and assemble them in some way, you can immediately write down the Hamiltonian that describes, this system, and it just contains this, single particle term that, in principle would drive Rabi oscillations, but then you have this interaction term, which gives you an energy shift to configurations where atoms sort of are nearby in Rydberg states. And as I said, a lot of these parameters of this Hamiltonian are can be tuned in a programmable way, in the sense that, for example, this Rabi frequency and the tuning are simply the parameters of your laser that you can change in an experiment in a time-dependent way. And the interactions between these atoms depend very much on where you actually place these atoms and which geometry you use to assemble your Rydberg atom array, which can be in principle also tuned, and experimentalists have developed amazing capabilities to essentially place atoms at positions at will in 1, 2, and even 3 dimensions. And where in the following, what I would like to do is tell you sort of what's the physics that is associated with this Hamiltonian, and it will depend very much on actually how I do place these atoms in which configurations I place them. And so to start out, let me just consider the most basic version, and which is sort of a 2D array of atoms on a square lattice. So imagine I can place atoms on a square lattice, in a regular square lattice, and I can choose the Rydberg blockade radius in such a way that it is just slightly larger than the lattice spacing of this square lattice, which means that I basically energetically forbid configurations where two atoms that are neighboring on this square lattice are both simultaneously in the Rydberg state. Okay, and so let me choose this configuration, which specifies my interaction part. And now let me look at this Hamiltonian, and let me look at it in sort of the two very, very simple regimes. One is if I take my laser detuning and I make it negative, so the laser has an energy which is sort of not quite enough to excite the atoms to the Rydberg state, what will happen is that the ground state of this sort of array of Rydberg atoms is very simply given by the state where each atom individually is in its electronic ground state. So this is a single snapshot from an experiment at Harvard where you can see a defect-free array of atoms where each of them is prepared in the internal electronic ground state, which happens to be the ground state of this Hamiltonian in this parameter regime. Okay, now you can, of course, change the parameters of the Hamiltonian, and for example, go to a, laser frequency, which is larger than the transition frequency from the ground state to the Rydberg state. So meaning, this should be delta larger than 0. So sorry for the mistake. So if the tuning is actually larger than 0, then, you can see that this Hamiltonian, you can lower the energy of the Hamiltonian by placing as many atoms as you can into the Rydberg state. Because each atom in the Rydberg state will lower the energy here by an amount delta. But of course, you can only put as many atoms in the Rydberg state as long as you sort of satisfy this Rydberg blockade condition. Otherwise, you would pay a huge energy penalty, and this would not give rise to a low energy state. So on this square lattice, you can immediately see that there are essentially two configurations where you can put the largest number of atoms in the Rydberg state while simultaneously satisfying this constraint, which are these two checkerboard configuration, where on every other side you have an atom in the ground state, which is here noted as sort of a dark green dot, and on the other sublattice, you have sort of an atom in the Rydberg state, which is sort of denoted here as a missing atom due to some of the readout mechanism in the experiment. So you can see that there are two, ground states in this case that break this translational symmetry. And you could sort of ask sort of how can I actually prepare these ground states here on the side where delta is larger than 0. Well, what you can do is you can, for example, perform some sort of adiabatic state preparation scheme where you start out with your Rydberg atom array prepared in the ground state at delta smaller than 0, where you can actually know the ground state and you can deterministically prepare it simply by loading each tweezer and optically pumping the atoms into the internal ground state. And then you turn on your laser that couples the ground to the Rydberg state. You turn it on at negative detuning, and then you slowly change the laser frequency in time, and you increase it to a point where the tuning is eventually positive and larger than your Rabi frequency. At which point your system, the ground state of your Hamiltonian would actually be this state. So if you do this slow enough, then your system will instantaneously follow the eigenstate of the Hamiltonian, and since you initialized it in the ground state, if you're slow enough and coherent, you will end up in the ground state on the other side, which is sort of how this picture is actually taken in the experiment. Of course, what's interesting is if you really look at the details of this process, if you look at this Hamiltonian at all these different times during this sweep, you realize that actually the system undergoes a second order quantum phase transition, which is expected, since on the right hand side of this sweep, when delta is large, your system breaks translational symmetry. So you expect that there is some phase transition which is in the 2+1 dimensional Ising universality class. But what it really means is that if you look at this Hamiltonian as a function of these parameters, and you start out on this end, you change your tuning to get to this regime, what will happen is that your Hamiltonian will have an excitation energy between the ground state and the lowest lying energy state, and this excitation energy will essentially vanish at the critical point where you have a phase transition between the disordered state on the left and the ordered state on the right. At the same time, your correlation length will diverge when you approach this critical point. And the way this gap closes and the way this correlation length diverges are determined by the universality class of this phase transition. So there's not really the microscopic details of this Rydberg Hamiltonian that determine this behavior close to the critical point, but it's really the universality class, which in this case is the 2+1 dimensional Ising model, that determines how this energy closes and how the correlation length diverges, which basically means it specifies this correlation lengths and dynamically critical exponents that are denoted here by Z and mu. And what happens is if you now make this parameter sweep that I indicated before, and you make it at different speeds, then you will eventually you do it at a certain speed, you will eventually become non-adiabatic with respect to this energy gap, essentially because the energy gap goes to 0. So to stay adiabatic, you would need to be slower and slower. So if you perform this quench at different sweeps, what will happen at different speeds? What will happen is that you will become non-adiabatic at different points in time during your sweep, and which will result in different sort of correlation lengths in your system at the end of the sweep. And this is sort of an experiment, experimental data doing exactly this. So you can see sort of the correlation lengths as a function of the detuning during the sweep for different sweep speeds. So if you make a very fast sweep, the correlation length essentially grows a little bit, but then doesn't reach beyond a certain point. If you make the sweep very much slower, the correlation length has much more time to adapt before you cross the critical point, and you reach a much more strongly correlated system after you cross the critical point. And this is an effect that's called sort of quantum Kibble-Zurek mechanism. And by careful analysis of how this correlation length in the final state actually depends on the sweep speed, you can infer the critical exponents, or relationships between the critical exponents of the universality class that describes the critical point of your quantum phase transition. And sort of this is this is just doing exactly this detailed analysis on this experimental data, where you can see that if you rescale your correlation length with your sweep speed and your your distance from the critical point in this way, then our Kibble-Zurek hypothesis essentially tells you that all these curves should collapse on a single line. And this is what indeed you observe, and they collapse on a single line, in particular if you use sort of the critical exponents here that correspond to the 2 + 1 dimensional Ising universality class, which sort of shows that here with this experiment you can actually probe this critical physics of this and check that this is in this universality class. So that's actually quite impressive, and as far as I know, it's the first time that critical phenomena, quantum critical phenomena in the 2 + 1 dimensional Ising universality class have ever been observed in an experiment. Of course, this is sort of the simplest case. This 2D square lattice with nearest neighbor blockade. Even on the square lattice, if you start sort of changing the blockade radius or changing the distance between these atoms, your phase diagram becomes actually much more rich. So what I talked about so far is sort of the transition at a certain blockade radius, which is just slightly above 1, from this disordered phase to this checkerboard phase. If you increase the blockade radius, you will generate or your system will host a couple of other phases, which are all sort of different, closest packing configuration on your square lattice. And you can experimentally probe some of them. And this has been done in this paper here by Sepper. But I'm not going to go into too much detail about that, because I would like to tell you sort of what other types of interesting physics you can observe if you now change from the square lattice to something like this lattice that I depicted here, where I placed now my atoms on links of the Kagome lattice. And this is something that in this Rydberg atom arrays I can very easily do. I mean, I essentially I cannot really do it, but my experimental colleagues just need to program where they would like to have their atoms and immediately change sort of the geometry. And so here I have a zoom into what this really looks like. So I have my Kagome lattice, and on each of these links, I have an atom. And now I can, of course, to specify my Hamiltonian, I do not only need to specify my arrangement of atoms, but also the blockade radius, right? And what I'm going to choose in the following is a blockade radius, which is 2.4 times the lattice constant, and it simply indicates that this atom here blocks all of these atoms in the circle. So if this is in the Rydberg state, none of these atoms in the circle can be in the Rydberg state at the same time. So why? So this would be a configuration, of that type. Where the red sort of circles indicate, a Rydberg excitation, and the white ones an atom in the ground state. So why am I interested in exactly this type of configuration? Well, for one, there is a very sort of nice mapping between, the configurations of these atoms that satisfy the Rydberg blockade and dimer models, dimer coverings on this Kagome lattice. So the idea is, what does this Rydberg blockade here do? It prevents, an atom here in this red circle to be in the Rydberg state if this red atom is in the Rydberg state. Now let me interpret the presence of a Rydberg excitation here by a dimer. Okay, so whenever there is a Rydberg excitation on this link, I draw a dimer on the same link. What does the Rydberg blockade now correspond to? Well, it means that if a dimer is on this link, there cannot be a dimer on this link, 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 or on this link, right? This is exactly sort of this Rydberg blockade constraint. So it means that if, you know, this dimer here, this dimer covers these two vertices, this one and this one. So if there is a dimer, there can be no dimer on the other ones, which means that this vertex can be covered by exactly only one dimer. Okay, so I have my Rydberg blockade constraint essentially corresponds to this constraint that I have at most one dimer per vertex of the Kagome lattice. And now if I, you know, go and choose my laser frequency to be, this delta should be again delta larger than 0, to be positive, then you know, my low energy configurations will be the ones where I have as many Rydberg excitations as I can while satisfying this blockade constraint. So these would be my maximum Rydberg density states, and they all correspond to different dimer coverings of the Kagome lattice. And now, in contrast to what you know you saw before, where we looked at the square lattice, where there were only two different configurations with the maximum number of Rydberg excitations that satisfy the blockade constraint. Now, in this kind of geometry, you suddenly have an exponential number of these, you know, configurations that all satisfy the Rydberg blockade constraint with the same maximum Rydberg density. So there is really a one-to-one correspondence between this Rydberg blockade physics and this dimer physics. And this sort of is promising to study sort of new types of, you know, quantum many-body phenomena. I mean, people have been interested in these dimer models for a long time, where, you know, in the 70s, where Anderson started to try to understand superfluidity, or try to come up with models to understand superfluidity. He thought about models where, you know, you have frustrated ferromagnetism on, you know, non-bipartite lattices like this triangular lattice. We have, you know, spins like a spin up and a spin down, but, you know, since the lattice is not, and they interact antiferromagnetically, but since the lattice is not bipartite, you cannot assign sort of the spin value here in a way that satisfies, you know, both antiferromagnetic links on these sides. And what he proposed is, well, maybe the ground state of such, you know, a system is actually something where, you know, these two spins here form singlets or dimers if you want, and you can now cover your lattice, for example, this triangular lattice, with, you know, different types of dimer coverings. And what he suggested is that the ground state of, you know, such a system might be described by what he called the resonating valent bond state, which is simply the equal weight superposition of all different dimer coverings of, you know, of the underlying lattice. And so why are people nowadays interested in these resonating valence bond states? Well, it's because these states have topological order. So this is a state that has no local order, but it has something like topological order, which I will comment on the next slide. You know, the states are highly entangled. They have non-zero topological entanglement entropy, and you know, that's why we're sort of interested in these states. So just, you know, to give you a sort of a flavor, where does topology enter here in these dimer models? Well, to see that, let us look at this lattice that I've introduced before. So where you have Rydberg atoms on links of a Kagome lattice, but let's change sort of the topology of the system a little bit by, you know, punching in here a hole, removing the atoms here in the central region, and therefore have, you know, defined this dimer model on a system where which is sort of topologically equivalent to a cylinder, right? There is sort of an inner boundary and an outer boundary, and you can go around this inner hole, you know, while staying on the surface. Now you can sort of write down different dimer coverings of this Kagome lattice with, you know, this hole in the middle, and you know, I've written down here a couple of them. And what you can do is you can, you know, take the you know, transition graph between two such configurations, and because of the dimer constraint, because, you know, you have exactly one dimer per vertex, you will see that the transition graph, which is just what you get when you add these two configurations modulo 2, that the transition graph contains only closed loops. Yeah? But now you can have closed loops that either do not encircle this hole, or you can have closed loops in the transition graph that do encircle this hole, right? So this transition graph between these two configurations does not encircle the hole. The transition graph between those two configurations, goes around the hole once, and therefore we can sort of naturally, sort the different timer configurations in different sectors, and in this case, two sectors that are basically, one sector is the one where I have configurations whose transition graph does not go around the hole or goes around the hole an even number of times, and in the other topological sector are the other configurations. And the point is that you have now many of these states in each sector, but these different sectors cannot be connected by local rearrangement of timers. So if you want to change from this arrangement, which is in the first topological sector, to this one, you actually have to change timers in a non-local fashion going around this hole, which is essentially the meaning of this transition graph. The other thing is, that the number of topological sectors that you can sort of have here depends on sort of the topology of your surface. If you would, for example, make another hole here, then you would get more distinct topological sectors, and that's sort of what allows you to have a model with topological order at the end. The last thing that is important is that these things cannot be distinguished by local observables. So if you can actually if you look at such a configuration only in a local way, you cannot tell whether it's in this topological sector or this one. What you have to do is you have to look at an observable that actually is a non-local one, like this string operator that counts the parity of dimers from the inner to the outer boundary. And it actually tells you whether you're in this topological sector or in the other one. But this is really a non-local quantity that quantifies, that tells you in which sector you are in. And sort of this structure of this timer Hilbert space makes it sort of natural to talk about topological order. And in particular, what you will have is, if you now have a Hamiltonian whose ground state is, for example, the equal weight superposition of timer coverings, like the one Anderson proposed, this RVB state, then now if you have a local Hamiltonian, if you now put it on such a geometry, you will suddenly see that your ground state will actually twofold degenerate, because you can have a superposition of all the dimer coverings in one sector and the superposition of all timer coverings on the other sector, and they will have degenerate energies where the degeneracy is sort of exponential in the size of this hole. So you will have a system that has degenerate ground state, very similar to what you have if you have traditional local ordered states. But now the degeneracy really depends on the topology of your system, and you cannot really distinguish the different ordered states by a local measurement. You cannot just measure here locally and see whether you're in this state or in this state. You would really need to measure a non-local order parameter. So that's what makes this superposition of timer states here topologically ordered. So that's a very nice relation between dimer states and Rydberg atom arrays, and sort of is promising to for us to look for topological order in these Rydberg atom arrays. So the question is really, can we generate these resonating valence bond state with these Rydberg atom arrays? I mean, the Hilbert space in this large tuning limit sort of coincides with this timer Hilbert space. This timer configuration space, but it's sort of not clear a priori whether you can generate exactly this state using this Hamiltonian that we have at hand. So first question that you might ask is, does such a state arise as the ground state of this Hamiltonian that I've written down with the precise configuration of the atom that corresponds to this Ruby lattice? And Ruben Veresen and Ashwin Vishwanath at Harvard have done this calculation on a sort of slightly simplified version of this Hamiltonian, and they indeed saw that as a function of this tuning, there is this trivial phase that connects to completely empty lattice, or the lattice where you have all atoms in the ground state. But then you have a finite parameter regime where you have, this spin liquid state, or this, which is sort of adiabatically connected to this equal superposition of all dimer coverings of the Kagome lattice. And then, of course, if you go to larger detunings, you will end up in an ordered state again, which is an ordered sort of a valence bond solid of dimer coverings. So this is really the state we were interested in. And we were thinking about sort of, how to prepare this experimentally. And, the idea is very similar to the one I showed you before. So what you do is you start out with the system in the ground state where you know it, where you prepare all atoms in the internal ground state. And then you change the parameters of the Hamiltonian in such a way that, you go to this regime where the ground state of this Hamiltonian is supposed to be this equal superposition of all these dimer coverings. So it's essentially the same as we did before on the square lattice, but now, for this different type of Hamiltonian where, you expect the ground state to be a spin liquid. And, you can do this, and then you can look at different experimental signatures of whether you're able to prepare this spin liquid state. First thing that you do is you look at whether your state, ends up in this dimer covering subspace. For that, you can sort of, for example, look at these loop operators where you take the parity of, the number of dimers across a closed loop. And if you're in the dimer subspace, this should be just, determined by the number of vertices that is enclosed by this loop. And what you see when you do this experiment is indeed there is a parameter regime where this expectation value of the Z operator that you can measure by sort of, taking single experimental snapshots, indeed signals you that you're in this dimer covering subspace. The next thing that you, of course, want to check is that you have coherence between these dimer coverings, and that's sort of requisite for this, that you actually generate this type of state. And to measure coherence, you want to measure an observable that actually connects different dimer coverings. Such an observable can be written down and defined like here, where you have, we call it X string. It's sort of defined in this pictorial way. So if you have a string on sort of the lower end of a triangle of this Kagome lattice, then it maps the empty triangle to the one where I have a dimer on the lower end, and it maps sort of the dimer on the left to the dimer on the right. And if you sort of define it in this way, you can see if you make a closed loop of this X operator, it actually maps dimer coverings maps one dimer covering into another one, which is sort of, and the two dimer coverings are related by sort of rearrangements of dimers around this loop. So if you can measure expectation values of this X operator, you can measure coherences between different dimer coverings. So it's kind of a little bit trickier how to measure this expectation value of the X operator. The Z operator is easy because you just take snapshots, and when you see a Rydberg atom, you say there's a dimer. When you see a ground state atom, you say there is no dimer. The X operator is more difficult because it's actually off diagonal in this measurement basis that you sort of can natively measure in the experiment. But what you can do is you can notice that you can sort of obtain this X string by actually conjugating the Z string by a unitary operation. And it turns out that the unitary operation that you need to map the Z string into the X string or vice versa is exactly generated by driving this Rydberg atom array resonantly with a smaller blockade radius. So what you do to measure it is you prepare your Rydberg atom array in the state that you want to probe. And then you change your Rabi frequency, which changes your blockade radius, and perform a resonant, quench with, a changed Rabi frequency, and for a certain time. And after that, you measure the Z string. And sort of this formula here that is written down only in a pictorial way, and that you have to believe me, tells you that if you perform this, operation, measuring the Z string after this rotation is equivalent to measuring the X string. So in this way, you can measure the X string and see that indeed it has sort of a non-zero expectation value for different loops. And in that sense, you can witness a coherence between these different dimer coverings. last thing that you can do is sort of a more sophisticated measurement of these BFFM order parameters. So you define expectation values of open X strings normalized by expectation values of closed X strings of twice the length, and similar for these Z strings that I've introduced before. They're just a parity of Rydberg atoms along a string. And what you expect is that if you're in the trivially disordered phase, this XBFFM parameter is non-zero. If you're in this valence bond solid phase, the ZBFFM order parameter should be non-zero. And if you're in the quantum spin liquid phase, both of them should be zero. Okay, and then this is sort of experimental results that shows this XBFFM order parameter and the ZBFFM order parameter as a function of the detuning. And you can see when you enter from the trivial phase, this XBFFM is actually non-zero, but it then approaches zero, which is sort of consistent with the fact that you transition from the trivially disordered phase to the quantum spin liquid phase. And the ZBFFM order parameter is actually always zero for the entire sweep, which tells you that in this gray area, you're actually in the quantum spin liquid phase. And what you can also see is that you cannot go to the valence bond solid phase, because there the ZBFFM order parameter would actually be non-zero. The reason why you cannot go there is because there is a first order transition between the quantum spin liquid and the valence bond solid, and the energy scales to resolve that and to actually prepare the valence bond solid are so small that it would require times and experiment that are beyond what you can do. Okay, so these signatures really make us confident that we can see here signatures of preparing exactly this type of spin liquid state. Okay, I'm a bit slow on time, but maybe this would be a good place to ask questions.
Okay, thanks, Hannes. We have a couple of questions on the more basic side, the introductory part to the Rydberg. So at which point do we have to worry about the size of the electron orbits becoming comparable to the separation between atoms? What changes if this becomes important?
Well, for this type of experiments, I mean, these tweezers are separated by actually, several micrometers, and the electron size, the orbit of the electron is much smaller than that. It's what is it, 100 nanometers. So there is really no, we are really not worried about that. And actually, if you would, you cannot really bring these tweezers much closer, because then you would get beating between the two tweezers, and you would get heating of the atoms. That's really not a regime where we want to be experimentally. Of course, if you could go there, you would start to see chemistry. Yeah. That's what you would see, and then it would be much more complicated.
Okay, thanks. When connecting to Rydberg levels, do we ever reach a regime where the usual dipole approximation for interaction with light breaks down because of the large electron orbit radius? What do we need to be careful of then?
Well, I'm not sure if dipole at the distances where we are interested in, I don't think the dipole approximation is. I mean, I don't think you can see corrections to the dipole approximations. What would you need to be careful if you? I've never thought about sort of corrections beyond the dipole approximations here, to be honest. So I would need to sort of postpone this question to maybe a later point.
Okay, another mean question. In all these basic Hamiltonians, one disregards motional degrees of freedom for Rydberg atoms. What are the requirements on motional states for current experiments? How cold do the Rydberg atoms need to be?
Yeah, okay, so this it's indeed true that we kind of completely disregard in this toy model that I've presented here, motional degrees of atoms, freedom of the atom. Of course, if you have motion of the atoms, the first thing that happens is that the interaction between two atoms in a Rydberg state becomes dependent. It depends on the distance of the atom. So if you have motion, the distance fluctuates, and you get dephasing due to fluctuations of the distance. That's something that we kind of avoid to a large degree because we work in this Rydberg blockade regime. So the only thing that matters here is that the interaction, which is much larger than the Rabi frequency, for example. So if the interaction actually fluctuates due to atomic motion, then that only gives rise to higher order corrections or terms that lead to dephasing. So this dephasing due to motion in the blockade regime is actually suppressed, which is why many of these experiments that work in the blockade regime are so clean. Of course, there are also different types of interactions that you can access in these Rydberg atom arrays that I did not talk about. I really talked about only blockade interaction that you get by exciting two atoms to the same Rydberg state. But there are also beautiful experiments done, for example, in Paris by Antoine Beauvais' group, where they excite to different types of Rydberg state and then have resonant dipole-dipole interaction. If you do, for example, that, then you're much more sensitive to the atomic motion, because there you really notice you're really sensitive to the actual value of the interaction, and then you can mitigate sort of dephasing due to motion, for example, by doing ground state cooling in optical tweezers. Several groups have shown that that's possible. At Harvard, in the experiment that I'm presenting today, I think we did not need to do ground state cooling simply because we work in this Rydberg blockade regime.
So how in these two regimes, how cold do the Rydberg atoms actually have to be?
I think in these experiments that I'm presenting here, they have, in these tweezers, there is a thermal excitation of sort of the vibrational degrees of freedom of a few quanta. So it's not thermally, emotionally in the ground state, but there's a few quanta of vibrational energy there.
Okay, well, let's maybe end the question break here and let you get back to your talk, and then we have a couple of questions at the end.
Okay, so this was sort of what I wanted to say about sort of many-body physics with Rydberg atom arrays, but you will see in a second that all I said is very closely connected to also a different application that you can use Rydberg atom arrays for, which is quantum optimization. But sort of before explaining the connection, let me just introduce a sort of a problem in optimization, classical optimization, that people from computational complexity theory are interested in. Sort of a paradigmatic problem, which is called this maximum independent set problem. So the problem is specified by by a graph. So I give you a graph, and I ask you to find the largest independent set on this graph. So an independent set is just a subset of vertices on this graph that are not connected with each other. So, for example, I've drawn here sort of two independent sets in red. So these two vertices are not connected to each other, so they are an independent set. You have another independent set, specified by these 4 red vertices. This is actually the largest independent set on this graph. I cannot find an independent set with 5 vertices. And so finding this largest independent set is actually a very hard task in general. So on this graph, you can still sort of convince yourself that this is the largest independent set. But if I write down a little bit larger graphs, you will have a hard time. And the reason is that this is actually one of the famous sort of NP complete problems, and even approximating. So finding approximate solutions to these maximum independent set problems is NP hard on general graph. And we would like to connect this problem now to Rydberg atom arrays. And the idea is the following. So we first want to find a formulation of this maximum independent set problem as a sort of spin problem, right? So we take our graph and we associate with every vertex a binary degree of freedom, or spin, if you want, spin 1/2. And basically, call the state 0, the one where the vertex is white, and the state 1 where the vertex is red. And then you can see that, if I write down a Hamiltonian of that type, then the Hamiltonian encodes the solution to this maximum independent set problem in the following way. So you have this Hamiltonian here has a part that simply counts the number of red vertices and gives each red vertex energy delta or minus delta, and it punishes configurations where two red vertices are neighboring to each other. So you can very easily see that if delta is smaller, the ground state of this Hamiltonian is just the one where all vertices are white. And if delta is sort of between 0 and V, then the ground state of this Hamiltonian is a state where the vertices that are form maximum independent set are red. Okay, so you can the ground state of the Hamiltonian in this parameter regime encodes the solution to this problem in this specific sense. Now, this is of course very much related to the Rydberg physics, because this Hamiltonian that I wrote down is essentially the same as the Rydberg Hamiltonian that I had before, with the difference that of course here I allow for arbitrary connections or interactions between arbitrarily distant vertices. So in a Rydberg atom array, what's much more natural is to consider something like a unit disk graph, which is a graph that I obtain by simply placing vertices on the 2D plane at random positions or at positions that I want, and connecting them by an edge if and only if they are within a certain unit distance. Okay, this specifies a unit disk graph, and I can ask, I can formulate this maximum independent set problem on these unit disk graphs. And one can easily show, one would first ask, well, is this problem on these unit disk graphs still hard, or did I make it easy now by restricting it to this specific class of graphs? And one can people have studied this in math 30 years ago and showed that this problem is indeed still NP complete even if I restrict it to unit disk graphs. So I can try and map any problem in NP, any one that I want, with a polynomial overhead to a unit disk graph, and the maximum independent set problem of the unit disk graphs tells me the solution of the problem that I was interested in to start out with. And this is of course now something very we talk about this graph because they have a very natural relation to Rydberg blockade physics, right? If I associate with each vertex now an atom, and with the red configuration a Rydberg state, then this unit disk graph simply encodes my Rydberg blockade constraint, and the maximum independent set would just be the ground state of the Rydberg Hamiltonian at large positive detuning. Of course, you have to be a little bit more careful if you talk about the actual Rydberg Hamiltonian that is not only sort of this, that has terms beyond the blockade approximation that I mentioned, but sort of I'm not going to talk about it in much detail. Let me just tell you, you can sort of find subgraphs of unit disk graphs, like sort of these graphs that you obtain by placing atoms on grids that are still NP complete, where this effect of the long-range Rydberg case is highly mitigated. Okay, so how can I now use these Rydberg atom arrays to implement quantum algorithms to try to find these maximum independent sets? Well, as I said, I assign an atom with each place in this vertex in this graph, and I choose my Rydberg blockade radius to be sort of the unit disk radius, and then I try to drive the Hamiltonian to drive the system in such a way that the system ends up in the ground state of this Hamiltonian. And so conceptually the idea is you initialize the state with all atoms in the internal ground state. You drive the system with this Hamiltonian, where you have sort of time-dependent control over some of the parameters like the laser detuning, the laser phase, and the laser Rabi frequency that sort of specify your unitary that you apply to your initial state. You get out a final state of this Rydberg atom array that is now parametrized by how you used your laser to generate this final state. And what you now can do is you can perform a measurement. You can measure each of these atoms. Is it in each of these atoms? Is it in the ground state or is it in the Rydberg state? And then you can sort of see, this will give you an independent set, and sort of, your goal is to prepare states with as many atoms in the Rydberg state as possible. So what you can do is you can perform a classical sort of feedback loop in which you now change your parameters, use a different protocol to generate a different state, and try to generate a state with a larger number of Rydberg atoms. Okay, so this is sort of the core idea behind all of these variational algorithms, and we can now use this type of approach to study variational algorithms and study their performance on this problem in an experiment. So the first thing that the first variational ansatz that we tried is inspired by this quantum approximate optimization algorithm that has been discussed in the literature since a couple of years. So the idea is to parameterize the unitary that I apply to my Rydberg atom array by a sequence of pulses. Each pulse here has a certain duration and a certain phase of your laser frequency, and in that way I sort of generate a unitary that is specified by so 2p numbers, where p is the number of pulses, and I can afterwards measure my system and sort of adjust my variational parameters until I'm sort of happy with the state that I reach. And so this is what they have done in the experiment on this graph. And what they saw is indeed that if you sort of take only one pulse, you get a certain approximation ratio. The approximation ratio is just sort of how big is your independent set compared to the actual maximum independent set of your graph. Sort of 1 minus the approximation ratio. If it would be 0, you would find the actual solution. So at depth 1, so if you have only one of these pulses, you reach an approximation ratio, which is sort of 1 minus r is around is a little bit over 0.3. But if you sort of increase the depth of the circuit, you can sort of lower and lower your approximation ratio, your approximation error, and get closer and closer to sort of the optimal solution. In the experiment, of course, you're eventually limited because you cannot go to infinite depth. What they see experimentally is that after depth 4, sort of the type of solutions that we can find with this variational algorithm does no longer improve, and there are a couple of reasons for that. One is, first of all, if you have a very large or very deep variational circuit, you need to find good good solutions for your variational parameters, and so the more variational parameters you have, the harder and harder this gets. So there is a difficulty of doing the classical optimization for deep circuits. On the other hand, one notices, because experimentally, if you make these sort of pulsed variational ansatz, these sharp pulses actually lead to many lead to blockade violations, so to excitations of Rydberg atoms on neighboring sites, which sort of drives you out of the independent set subspace, and sort of this is sort of a limitation of this generic pulsed ansatz that you can see here in the experiment. So what we did is we changed the variational ansatz to something that is more inspired by this adiabatic algorithm that we also used before to prepare these different types of Manybody ground states. The idea here is to choose a sort of an initial detuning and a final detuning, and interpolate between these two detunings with a certain function that you can now specify by a couple of sort of variational parameters, like your intermediate detunings and the times at which you reach them. And if you smoothen this out, you now get sort of a smooth, variational ansatz for the function that specifies your unitary. You can sort of define an effective depth for this circuit by basically saying, okay, how long do I, what's the total time of my unitary evolution in terms of, for example, the pi time that is required to flip a single atom. And then you can do exactly the same sort of variational optimization of these pipes of all these parameters. And what you can see is that you can, with this type of variational ansatz, you can actually improve your approximate solution, the one that you find, quite significantly over, the pulsed one that we saw before. One reason is that it's smooth. You don't have these sharp edges. You don't get so many you don't get driven out of the independent subspace so much. The other one is that you can, you can find very good, variational solutions with much fewer variational parameters. So for this type of pulses that you use here, only 3 or 4 variational parameters are actually necessary to reach approximation ratios, which are here above 90% for this type of graphs. Okay, what you can then now also do is really do a systematic study of the performance of this algorithm on graphs of different sizes, and we've looked here at graphs that range from 80 atoms to something close to 300 atoms. And if you use different graphs that are all generated according to this sort of to this square lattice with diagonal, what you can see is that many of these graphs actually have multiple solutions, and there is a degeneracy in the ground state, and this degeneracy actually determines how well your approximate quantum optimization algorithm works. So if you plot, for example, here 1 minus the approximation ratio versus the degeneracy density, which is simply the logarithm of the number of optimal solutions divided by the system size, you can see that across all system sizes that we can try for this type of graphs, we actually see that the approximation ratio collapses on this universal line, and that relates it to this degeneracy density. We can now go ahead and sort of ask, okay, maybe I'm not only interested in the approximation ratio, but maybe I'm interested in actually finding the exact ground state of this maximum independent set problem, and maybe I'm interested in comparing it with a classical algorithm, like, for example, simulated annealing. And so that's what we did here. We looked at a classical simulated annealing algorithm, where we sort of selected graphs that are very hard for simulated annealing, where we identified a hardness parameter, which is essentially telling you how many sort of optimal solutions do I have, compared to the number of solutions that are almost optimal. So how many global minima do I have compared to the number of local minima? This is what sort of determines the hardness for a simulated annealing algorithm, or for the type of simulated annealing algorithms that we considered. And sort of we ran simulated annealing, and we saw this dependence on the approximation ratio or the performance on this hardness parameter. On the other hand, we run the same graphs on the quantum machine, and what you can see is that sort of for these hard instances that are very hard for the simulated annealing, you actually can see that the quantum machine has a different performance, relates differently to this hardness parameter. And you can see the harder your problem becomes for simulated annealing, the sort of the more you gain by doing sort of your quantum algorithm. And so essentially what we're saying here is that the parameter that determines the hardness of simulated annealing affects the quantum algorithm in a different way. And so if you want to understand what actually determines the performance of the quantum algorithm, you can, what you expect is that actually it's maybe not necessarily just this, number that, specifies the classical solution space, but it's actually the gap along this sort of, adiabatic annealing path, or the minimum gap along this adiabatic annealing path. And experimentally, you can even measure sort of this minimum gap by performing sweeps where you slow down at different points in your detuning sweep, and in this way you can you see that if you slow down at the point where your energy gap is small, you should get sort of the best solution, so the highest probability of finding the actual ground state. And that's indeed what you can see here. So this is an experiment where you see data where the experiment slowed down at different tunings, and indeed when the gap is minimum, the probability of, when you slow down at the minimum gap, the probability of finding the actual maximum independent set is largest. And so this is a systematic comparison between the minimum gap over different graphs, over these hard graphs, and how it relates to the probability of finding the solution in your quantum annealer. And indeed, you see that the machine and the performance of the machine correlates very well with the minimum gap, which sort of in that sense determines the performance of this quantum optimization algorithm. Okay, with this, I'm sort of very close to the end of my talk. I have a last part, but maybe it's a good point to get a few more questions.
Yes, so we have one from Jin Zhang, who asked still about the earlier part, but I think we should start with that. Besides the snapshots of the spin liquid state, is it possible to measure other quantities, such as topological entanglement entropy?
In principle, yes. We didn't do that in that experiment, but in sort of this last part of my talk, I will tell you, I will come exactly and explain how one could in principle measure entanglement entropy in these systems. And there are different approaches. One could do some sort of almost state tomography by doing random local rotations, for example. There are protocols that have been developed, for example, by the group of Peter Zoller, and that have been implemented with trapped ions, for example. But one could sort of imagine to implement similar protocols also for Rydberg atom arrays. The way we measure entanglement entropy in these Rydberg atom arrays is actually by interfering two copies and measuring sort of Rayleigh entropies by sort of the swap trick. And that would be one way in which one could imagine to measure entanglement entropy and really see sort of this fingerprint of topological order in the topological entanglement entropy.
Okay, so let me jump to the annealing, the last part. Can you say a bit more about having to check for the minimum gap in the annealing algorithm? How can this be done if you don't know the solution a priori?
Yeah, well, you could in principle, if you don't know the solution, in all these experiments that we've performed here, we knew the solution a priori. If you don't know the solution a priori, there would be some ways in which you could, in principle, imagine to find the minimum gap. In a way, what you could do is you could, perform a sweep, and as I said, kind of try to slow down at different points in your sweep, and in that way you can, determine the location of the minimum gap, because if you slow down at the point where the minimum gap occurs, then sort of you expect your solution to be, better than if you slow down at the point where your minimum gap, where you're not at the minimum gap. So in this way, you could, in principle, you can determine the location of the minimum gap even if you don't know the solution of your problem. And if you're really interested in the size of the minimum gap, you could, for example, go to, with your system, with your Hamiltonian, to the point of the minimum gap where you sort of located it and do something like modulation spectroscopy to actually see, at which frequencies do you excite the system.
But that would still require a way to check the solution, right?
I'm not sure. You could, if you can show that. If you can show that if you slow down at a specific point in parameter space, and that really improves upon your solution, then it's very likely that the gap is small. And to see that your solution improves, you don't necessarily need to know the exact solution. Of course, this is sort of not a rigorous statement, but that's how I would do it in practice. but yeah.
Okay, so in the variational algorithms, especially as the problem size becomes larger, to what extent is the bottleneck trying to find good classical optimal results for the variational parameters?
That's a good question. I mean, for this, it depends very much on how you parameterize your variational, what kind of variational manifold do you use. One good thing about this type of unit disk graphs that we looked at is that what you find is that very often the best variational parameters that you have for one problem or for one graph also are good variational parameters for another graph. So I think that really has to do with the fact that these graphs have a certain locality, and that therefore is sort of your solution, your optimal solution of your variational problem sort of concentrates around a certain, typically trajectories, and that helps very much.
In terms of real-world applications, how restrictive is the polynomial overhead of mapping a problem to the unit disk graphs? It doesn't change the complexity class, but do these polynomials still provide a large overhead that will take some potential applications out of reach?
Well, I mean, we're working now on actual encodings where you can encode, for example, arbitrary Ising problems with all-to-all connections, or maximum independent set problems on arbitrary graphs, or even sort of factoring of integers if you want in these unit disk graphs, and the overhead is always quadratic. Okay, so if you have an arbitrary Ising problem, you can encode it in an Ising problem on n vertices. You can encode it into a unit disk graph with n squared vertices. So the overhead, this polynomial overhead, is rather modest for many of the applications or many of the problems that you're actually interested in real world, like sort of Ising spin glass and things like that.
And on the same subject, a question by Thomas Kosley: what industries could you see benefiting from solving this type of problem on unit disk graphs?
Well, I think that, there are some sort of applications where unit disk graphs are really relevant, like sort of when you try to design wireless networks and try to figure out where you should, position, antennas, because there you sort of have to have a natural sort of unit disk or 2D geometry. I think in terms of, real world applications, I think it's really, as I said, much more interesting once you go to sort of problems that don't have this, 2D geometry or this unit disk geometry, and then I think you can map everything to unit disk graph with quadratic overhead. So as long as you can formulate it, the problem of interest as an Ising problem, then I think you're in the game here with these Rydberg atom arrays.
Okay, maybe one more question before I let you finish the talk. In terms of making these optimization routines useful, there's an ongoing competition with the development of classical, probabilistic, and heuristic methods. Do you see prospects for analog quantum devices to win this competition in the coming years, or will we need fault-tolerant digital quantum computers?
I think to actually beat the best classical optimization algorithms will be very hard without sort of improving dramatically on the coherence times, because even if you can go to system sizes where you classically optimizers struggle, I think the coherence times that you would need to solve these problems with a quantum machine are just beyond what we can do right now. So I think there needs to be a further step in technology before these systems actually can sort of really outperform classical machines on in real life. And I'm not sure if sort of fault tolerance is the answer, or if the answer would be more find ways to make these systems more coherent, or go to different, for example, go to different types of Rydberg states, like circular Rydberg states that are intrinsically have a longer lifetime. I think that's a little bit the questions that I find interesting. So where do you really push this platform in order to go to longer coherence times that are necessary to really make these things useful? Sorry.
Well, I'm very happy to hear about the interest in circular Rydberg states, and I think with this you're good to go for your last
okay.
part of the talk.
So I think I have sort of 5 more minutes maybe. So I'm going to be very brief on this last chapter. But what I would like to also discuss is a different way of using Rydberg atoms to actually do quantum information processing. And to do that, let me sort of switch a little bit the setting. So far, I talked about a Rydberg atom as a qubit where I have a ground state and a Rydberg state, which are my 2 qubit states. But of course, I can make use of sort of the rich internal atomic structure and define, use 2, for example, hyperfine states or 2 metastable ground states as qubit states, and then just use the Rydberg state as an ancillary state to perform interactions between these qubits. And of course, this has sort of set of advantages. Of course, this type of hyperfine qubits have really excellent coherence properties. You can really do high fidelity single qubit rotation and readouts. But what you will see is, one nice aspect of this thing is that you can trap these atoms in these hyperfine states, and or these hyperfine qubits, and coherently move the atoms around with these tweezer arrays, and dynamically sort of rearrange your connectivity of your quantum processor. But just before doing that, let me just explain you how you do actually Rydberg gates between qubits of that type. So there's an idea that is now already 20 years old that basically exploits this Rydberg blockade mechanism to make a controlled phase gate between 2 atoms or 2 qubits that you encoded in these atomic states, as I discussed. And the idea is, you perform a sequence of pulses where you first perform a pi pulse on a control atom, and then 2 pi pulse on a target atom, and then a pi pulse on the control atom again. And what happens is that this should be a controlled phase gate, which you can see by just working through the different options. So if you start out with both atoms in the 0 state, all of these lasers do nothing to the atom, and the 0, 0 state gets mapped to the 0, 0 state. If you start out with one atom in the 1 state and the control atom in the 0 state, the first pulse does nothing. The second pulse, gives you a 2 pi rotation of your target atom, so you pick up a minus sign, and the third pulse does nothing. So you end up with sort of mapping the 0, 1 state to minus the 0, 1 state. Similarly, if you start out with the 1, 0 state, you will effectively perform a 2 pi rotation on one of the atoms and end up in the same state as you started out with. So you pick up a minus sign also here. The interesting thing is, of course, if you start out with the 1, 1 state, then the first pi pulse brings your first atom to the Rydberg state, which sort of due to the Rydberg interaction, now this transition has a different energy, and the second 2 pi pulse on the target atom, does nothing, and so the third pulse brings your control atom back to the 1 state, and so in total you just picked up a sign of -1 for this effective 2 pi rotation here, while this did nothing. So you again end up in the state that you started out with. But you now also get a sign of -1. So in total, this is exactly the definition of a controlled phase gate. People have done this in experiment, and what we did recently is we cooked up sort of a variant of this gate where you in contrast to what I just described, you don't need. What I described actually needs local control of each atom, right? You need to make a pulse on the first atom, and then a pulse on the second atom, then a pulse on the first atom again. You can perform this controlled phase gate also just by globally driving both atoms without local addressing with the same sort of laser. And you can show that if you make 2 pulses with a laser with the proper Rabi frequency and the proper detuning, you actually implement a controlled phase gate. And this has then been implemented in the group by Michalukhin at Harvard, and they've reached fidelities sort of in this first experiment that are beyond 95%. And if you correct for state preparation and measurement error, you can even reach fidelities even a little bit higher. So that's really promising, because now you can sort of think about combining this building up circuits by for example, having atoms in optical tweezers and moving these tweezers around to bring 2 atoms close together, and make controlled phase gates between them, and then rearrange the configuration of the atom and sort of connect atoms that are sort of further apart. This has been done in experiments by Twolevel Prüfstein here was the lead author, and they have showed that using this controlled phase gate that I just described, you can entangle, for example, 2 atoms and then move them far apart, and still sort of preserve the entanglement between these 2 atoms even after you have separated by a distance. This you can see by, for example, looking at 2 atom parity oscillations, and this works actually. What they've shown is that this works, quite independently of the speed at which you move these atoms around, as long as you sort of stay below a speed where you would lose the atom from the tweezer. And with this kind of toolbox, you can now start to build very, variety of states. But, for instance, you can sort of try to build a 1D cluster state by, entangling 2 atoms with a controlled phase gate, and then, entangling atoms in parallel here, and then moving, this second atom, next to the third atom, like depicted here, and then sort of entangle sort of in a second step the atom 2 with atom 3 and atom 4 with atom 5 and so on. And so in this way, you can, in a 2-step process, realize, for example, a 1D cluster state. And sort of this is the experimental result that did exactly this. You can do even sort of fancier things. You can, by this dynamical rearrangement, generate a state which is, equivalent to the toric coat state, actually on a torus. And the idea is that, you take atom, entangle them using sort of this controlled phase gates, and then you can generate, toroidal boundary conditions by moving some of the atoms, around to the other side, and entangle them with sort of the atoms at the other boundary. So you can see with this dynamic rearrangement, you can actually, overcome sort of, the restrictions of what you typically would have on the 2D plane. And I think it's really an amazing sort of inspiring experimental development that, can really highlights the features of this Rydberg atom array platform. And just on my last slide, I to connect to one of the questions about how to measure entanglement before, we actually proposed and did then an experiment exactly along these lines, where we prepared some Manybody states of our Rydberg atom array with some sort of by using a Hamiltonian dynamics to generate some states. We actually did it on 2 copies, and then we used these controlled phase gates to perform Bell measurement on the 2 copies. So this is a pictorial description here. You have your atoms in an array, you have a second copy of it. You use your Hamiltonian to generate some interesting Manybody states of this atom. Then you bring the 2 copies together, and you perform Bell measurements between each atom and its pair, which essentially boils down to performing a controlled phase gate between each atom and its pair, and then you read them out. And you can show that if you analyze, if you interpret the measurement outcomes of such a measurement correctly, then you get access to the purity of your system, or the purity of reduced subsystems of your total Rydberg atom array, and that in turn gives you then access to things like entanglement entropy or Rayleigh entropy of subsystems. And we've shown this for 2 different types of problems. One is just quench dynamics, where you see thermalization of some sort of generic initial state, where after a while your entanglement entropy satisfies, a generic volume law. And we also started to look at entanglement entropy for states that undergo this quantum scarp dynamics, which is sort of non-ergodic dynamics in an otherwise chaotic system, where you expect that your entanglement does not, obey a volume law, but rather grows much more slow, and eventually these states should obey an area law. And this is indeed what we can observe, for example, using this, this combination of gates and dynamical rearrangements in combination with sort of analog quantum simulation. Okay, with this, I think I'm really out of time. I would just like to, thank, my collaborators at Harvard, in particular, sort of this experimental team that, did all the work that went into these amazing experimental results. The PIs that were leading the experimental effort, but then also sort of my theory collaborators that, I were too many to actually, show a picture of all of them. Yeah. Okay, thanks.
Thank you very much, Hannes, for this very comprehensive overview. So on the last part, in the toric code implementation, you had mentioned on your slides that there's dynamical decoupling. What is this needed for? Actually, was one earlier. Yeah, there.
Well, you use dynamically decoupling. Essentially, it's a technique for fighting sort of natural dephasing mechanisms of your hyperfine qubit. You get sort of differential light shifts from your tweezers, and you use a dynamically decoupling scheme to essentially protect the coherence of your hyperfine qubit.
Okay, and then maybe the very final question, kind of a big picture question. What is the biggest single challenge in building a useful future fault tolerant quantum computer with Rydberg arrays?
Oh, that's, I guess, yeah, it's an important question, but it's kind of difficult to answer. I think, I think that, progress has to be made on sort of several steps, from sort of, readout to, coherence of your qubits. But I think right now, the next big step would really be to actually design, gates that are robust against certain types of, noise mechanisms that are, present in the experiment. I think that would help a lot. If you really want to go to deep circuits, I think you need to have sort of more high fidelity gates. I think from a theory side, what you can do is really either explore, better gate designs, or go to, try to use, different types of Rydberg states, like the circular Rydberg states. I think from an experimental point of view, a lot, comes down to having better lasers. I think that would sort of make a big difference, and I think made a big difference in the past in the development that you saw, that one could see over the last, 10 years of this Rydberg atom arrays as a platform. Just the fact that, people develop better lasers, help to push these fidelities quite a bit.
Okay, so I think we have work to do on both the experimental and theory side. This is a good point to stop. Thanks very much, Hannes, and I hand over back to Andrew.
Yeah, thank you very much also from my side, Hannes, for the really nice and comprehensive overview of what's happening with Rydberg arrays at the moment. And thank you to everyone for joining us. So we'll be back with the Quantum Science Seminar next month again, first Thursday of the month. That will be the 5th of May, and our speaker will be Ulf Leonhardt. So we're looking forward to that. In the meantime, do also check out our sister seminar, the Virtual AMO Seminar. They're giving seminars every couple of weeks, and the next one will be Friday of next week, the 15th of April, where Alexandra Landsman from Ohio State University will be talking about photo emission delays in molecules. In the meantime, to keep being notified, please do check out quantumscienceseminar.com, subscribe to our mailing list. Follow us on Twitter, subscribe to the YouTube channel, and we'll look forward to seeing you all next month. Meantime, have a nice rest of the month and see you next time. Bye.